in the Lagrangian formulation, you remember the definition of the cyclic coordinates. Cyclic coordinates are the ones which do not appear in the expression of the Lagrangian. That means, Lagrangian is not explicitly dependent on a particular coordinate, we mark it as a cyclic coordinate. Now, in the Lagrangian formulation, the Lagrange's equations which is d by dt of del L by del q j dot, this is equal to del L over del q j, and this is of course for each j. Now, if your Lagrangian is independent of a particular q j, then of course the right hand side becomes 0, and so if L is independent of some q j, this immediately implies that d by dt of del L by del q j dot, and remember this is nothing but in our definition p j dot is equal to 0, giving you the conservation of p j. So, this remains constant throughout the motion of the system. Now, we want to do the same thing in the Hamiltonian mechanics or Hamiltonian formalism. In the Hamiltonian formalism, remember we have two equations, which is q j dot is del h over del p j, and the second equation. So, this is in the Hamiltonian formalism, Hamilton's equations, and you have p j dot which is equal to minus of del h over del q j. So, the same thing would actually apply here, and you remember this in fact was nothing but del L over del q j. While deriving the Hamilton's equation, we have gone through this stage, and remember this also means that if a particular coordinate is cyclic, it is not appearing in Lagrangian, then it also will not appear in Hamiltonian, and which automatically gives you the conservation principle, because p j dot in that case would be 0, leading you to the same conclusion there. Okay. So, in that case p j would be a conserved quantity, and consequences of this in terms of various rigid motions or rigid transformations was, suppose one of the coordinates q j is say coordinate of or one component of center of mass. If it is a component of center of mass, then when you transport the center of mass without changing the other coordinates, that amounts to a rigid transformation. That means, it will just translate along that particular direction, the center of mass along with the entire system would translate in that direction. And if this coordinate is cyclic, what does that mean? That means the linear momentum or the component of the linear momentum in that particular direction is conserved. Okay. So, this is the standard Noether's conservation theorem. Same thing would apply for if you have a system and one of the coordinates there describes a rigid rotation. Okay. That means, when you change this coordinate, the entire system simply rotates. What happens in that case? If this coordinate is cyclic, then your angular momentum is conserved. So, these two principles, the Noether's theorem, we had already seen is simple consequence of Hamilton's equation 2. It is the same principle that would apply here. Equations. Okay. So, everything that we discussed in Lagrangian formulation would simply apply here as is. So, I am not going to derive those expressions again, but this here makes the connection very clear that the partial derivative of q j, partial derivative of Hamiltonian with respect to q j is also equal to partial derivative of Lagrangian with respect to q j, but with an additional minus sign but that immediately tells you that a cyclic coordinate for a Lagrangian is also a cyclic coordinate for the Hamiltonian system. Okay. Now, I will write down the time dependence. Remember, if you take Hamiltonian is function of q, p and t. So, if I take a total derivative of h with respect to t, then dh by dt will be equal to partial derivative of h with respect to q into q dot plus partial derivative of h with respect to p into p dot and plus del t. Now, what is partial derivative of h with respect to q? But that is nothing but minus p dot, and what is this here? Oh, that is nothing but q dot. So, what will happen? The first two terms will cancel each other and this only becomes pi del t. And remember, this was also equal to minus del t. Okay. Similarly, the Lagrangian, if it is independent of t, Lagrangian is independent of t. By that what I mean is that the Lagrangian does not explicitly depend on t, then the corresponding Hamiltonian is also independent of t. And what does that mean? That immediately means that Hamiltonian is a conserved quantity. Or the value of h will remain constant throughout the motion of the system. Now, this is a simple consequence which is exactly same as what happened in the Lagrangian case too, but the difference here is in case of Lagrangian, the conserved quantity is the energy function, and remember the sort of deceptive similarity between energy function which we denoted by small h and the capital H which is Hamiltonian here, they are defined over different spaces, but the consequence is still same. The H is independent of t, Hamiltonian is independent of t, Hamiltonian is conserved quantity, Lagrangian is independent of t, energy function is a constant of motion. Okay, fine. Now, you see the connection between Hamiltonian and total energy is also deceptive, and that also does not depend on this particular fact. So, whether H is conserved or not, and is H also the total energy? These are two separate questions. Okay? They can be independently answered. So, it may happen that Hamiltonian is total energy and is conserved. It may happen Hamiltonian is total energy, but it is not conserved. It may happen that Hamiltonian is not total energy, but it is conserved. So, all possibilities are there. These two questions are completely independent from each other, and that also brings us to slightly different discussion in this connection. See, the Lagrangian is a scalar function defined over configuration space. Now, what happens is this: when you change the coordinate system or make a coordinate transformation to new set of generalized coordinates, what you are doing is you have a point, it is given by a new coordinate. Now, what happens to the scalar, the value of the function Lagrangian? Well, that remains same. So, the value of Lagrangian, I will in fact note it down here, that value of the Lagrangian does not depend on the coordinates. Okay. So, all you have to do is from given Lagrangian, its functional form of course would look different, but if you calculate the actual value, that will remain same. Now, when you come to Hamiltonian, Now, this thing does not hold. You see it, the Hamiltonian is a scalar function which is a Legendre transform of a Lagrangian. Now, what will happen is this: if you change the coordinate system, the Lagrangian's functional form changes, and then the Legendre transform of that could be completely different. Okay? And there is no connection between the first Hamiltonian and the second Hamiltonian. Of course, we can find the difference between the two Hamiltonians, but they could look completely different. Not just they look different like Lagrangians do, their values at a particular point in the space also changes. Okay? And the consequence is because a very simple fact. Remember, we did not calculate Hamiltonian, which is function of q p t, by simply taking Lagrangian and take q, substitute q dot by q p t and t. So, what I could have done was this: if I want to define a scalar function on the phase space, which is derived from the Lagrangian defined over the configuration space, I can follow a simple strategy like this there. So, you take q dot, you already have Lagrangian, substitute q dot by function of q p t, but that is not what we do here. This is not how Hamiltonian is defined. The Hamiltonian is defined as p q dot minus L, that is Legendre transform, and that means every time you make a coordinate transformation, you get a different Hamiltonian function. This is exactly same as the energy function. Remember, the energy function depends on which frame you are sitting in. So, if you for example take a simple example where you see a car passing by on the road with some uniform velocity v naught, say, you would say its kinetic energy or its total energy is half m times v naught square, m being mass of the car. But if you are sitting inside the car, then of course the car is stationary. What is the energy of the car now? That is 0, as simple as that. So, energy function of course always depend on which inertial frame which coordinate frame or which reference frame you are sitting in. Different reference frames will give you different answer for the total energy. Not for the Lagrangian. Lagrangian of course will give you always the same answer irrespective of which coordinate frame or reference frame you are sitting in. Okay. So, let us see one example which illustrates the ideas that we were just now talking about. So, let me take the example of, say, there is a, so let me draw the coordinate system first, and let us say there is a some sort of a cart here, and this cart can say roll on the, and you have this block here, okay, which is connected by the spring, and the cart is of course massless. So, the cart is massless. So, we will just put it out of our calculation, and the block has a mass of m, and we will assume that this cart is moving with uniform speed v naught. Okay. And on that cart, then the block sort of does some motion because of the spring there, and let me put this coordinate as x coordinate, and the left end of this I will. So, instead of taking this as x, remember, if this is the neutral length somewhere here, if this is your neutral length, I will take this distance as x prime. Okay. Now, sorry. So, let me rewrite this. This distance of course will be v naught times t. Let us assume that the left end of the cart was on the origin or at x is equal to 0, at t is equal to 0, that means this particular point would have moved by v naught t in time t, and I will call this extension here by coordinate x prime. Okay. Now, let us start doing the calculation for this. First of all, remember, we will assume that the ground frame is an inertial frame, but if the ground frame is inertial frame, what is the cart frame? That is also inertial frame, because cart is moving with a uniform speed v naught. Okay. So, the Lagrangian, so the equation of motion of course should look exactly same in both cases, they are inertial frames, remember, but the Lagrangian L first written in terms of the x coordinate, this will be minus. So, the potential energy is half, there is a spring constant, into the extension, that is x minus v naught whole square. Okay. What are the equations of motion? We can immediately write that down. So, equation of motion will be equal to mx double dot is equal to minus k times x minus v naught. This is not of course surprising. The equation of motion is just that of a spring motion there. Okay. So, whatever extension is there, the acceleration would be about the same. What would be the equation of motion in terms of x prime? Remember, the transformation from x to x prime is time dependent. So, x prime is equal to, or x is equal to, let me write this as x prime is equal to x minus v naught t. Okay. So, this transformation is of course time dependent, but this immediately tells you that x dot double prime x dot prime is nothing but x double dot. What would happen to the equation of motion? Oh, simply m x double dot prime would be equal to minus k, and we of course know x minus v naught t is x prime, and this is to be expected because both the frames are the inertial frames. Okay. What is the Lagrangian in terms of the x prime frame? So, the Lagrangian here also can be transformed. Remember, because of this equation, now we will have half m x dot plus v naught. So, if I take a time derivative of this equation, I will get x dot is equal to x prime dot plus v naught. So, that will be square and minus half k, but this transformation is nothing but x prime squared. Look at the two Lagrangians. This Lagrangian here, the first one is time dependent, there is an explicit time dependence here. This one is time independent. Okay. All right. So, here in the first case you do not have the energy function conservation, but in the second case you have energy function conservation. Okay. Let me write down the Hamiltonian for each one of them. So, the Hamiltonian, which is function of x, and I will write it as p t, this would be equal to, remember x dot just appears here in the x dot square. So, the transformation of this L is more or less straightforward. We can use one of the techniques that we have used earlier for the quadratic Hamiltonian, quadratic Lagrangian. So, this will be equal to p square by 2 m. If you want, I will also write p here, p is nothing but m x dot. So, it is p square by 2 m plus half k x minus v naught t whole square. Lagrangian is time dependent, Hamiltonian is also time dependent. Okay. And what is this quantity? Is this quantity total energy? Yes, it is a total energy as seen by the ground frame, Okay. Is this Hamiltonian function conserved quantity? This is a total energy, but is this conserved? It is not conserved. Why? Because it is time dependent. Okay. And physically, do you see that it is not really time, the energy, total energy is not conserved in this case. See what would happen in this case. Suppose there is no force which maintains the speed of this cart as V naught, then what would happen? When the blob moves this way, so then in that case there would be no external force. So, when the block moves this way, the cart would move that way and the opposite. Why? Because the center of mass is not moving anymore. Okay. In that case, so when the actual system, whole of the system is moving with V naught t, to maintain that speed V naught, we must exert an external force, and this external force would of course be doing some work on the system. So, of course, the energy will go in and out of the system as the block moves on the top of the cart, but that is what will happen. The total energy, it is a total energy seen by the ground frame, and it is function of t, or I will say it is not a constant of motion. Okay. Fine. Now, let me calculate Hamiltonian for the second case. So, the Hamiltonian for the second case. Now, for the second case, what would be your P prime? P prime will be m times x dot plus V naught. Okay. Just take a derivative of this with respect to, so derivative of this with respect to, and again it is a quadratic function. So, we can immediately calculate the Hamiltonian as a function of x prime, p prime and t, and in this case the Hamiltonian will be p minus m v naught whole square by 2m and plus half k times x prime square. Okay. How did I get this? Because you see p prime has, so in this Lagrangian here, there is a linear term in x naught, x dot, and remember that technique that we have developed, it is p tilde minus a tilde. So, of course, that linear term will subtract from here, the coefficient of the linear term will subtract from here and you will get this. Do calculate this yourself to find this. Now, what is this? This Hamiltonian is a total energy seen by the cart frame. It is a total energy seen by the cart frame. Okay. In the cart frame, that you can immediately see, this p minus m v naught is in fact just mx dot, sorry, I forgot to write the prime there, mx dot prime. So, this term here is in fact just equal to half m x dot prime squared plus the spring's potential energy. So, this is just the potential energy plus kinetic energy of the block as seen by the cart. Is this constant of motion? This Hamiltonian does not depend on t, it is independent of t. Okay. It is independent of t, and so this one of course will have an extra constant term, but apart from that, and this is a constant of motion. Okay. So, this clearly illustrates, look at this, I will in fact would like to now mark this as h prime. See, the Lagrangian holds its value or keeps its value when you go from one coordinate system to another coordinate system. Now, the Hamiltonian, look, this Hamiltonian here is not a constant of time, it changes with time, and it is actually so there will be this Hamiltonian here is constant of time. So, there is no way these two quantities are going to be same or equal. So, this is how the energy conservation or conservation of Hamiltonian is a separate question from what that Hamiltonian represents. That Hamiltonian may be representing total energy as seen by one frame or total energy seen by the other frame. Total energy, remember, depends on the reference frame that you use. Okay. Now, there are more advantages of doing Hamiltonian mechanics. In general, from the computational point of view, the Hamiltonian actually does not offer any additional benefit. When you actually sit down to solve these 2n differential equations which are first ordered, you invariably end up with the second order differential equation, because you would eliminate p variable. So, computationally it does not make much sense, but when there are cyclic coordinates, then something nice happens, and then we may be able to reduce the number of equations using the conserved quantities there. That I will discuss in the next section. This procedure is called as a Routh's procedure. So, after having written down the Hamilton's equations, you see what we have done is thus. We have replaced the n second order differential equations by 2n first order differential equations. But does that mean that you actually have achieved some computational ease, is the question. We definitely know that when you go from Newtonian mechanics to Lagrangian mechanics, especially in constrained systems, you definitely have a great advantage of computability, but going from Lagrangian formulation to Hamiltonian formulation, there is actually not much of a computational ease. What happens is invariably you will end up solving the second order differential equations instead of the first order differential equations. So, when does this become useful, the Hamiltonian formulation? Of course, Hamiltonian formulation we learn in physics for many other reasons, but when will this become actually useful for calculation is in one case, when there are cyclic coordinates. Okay. Let me write this down. So, let us assume that in a system one of the variables is cyclic. Okay. So, you have a system with n degrees of freedom, and one of them I am going to say the last one q1 is a cyclic coordinate. If it is a cyclic coordinate, we know that the corresponding conjugate momentum, that is P n given by del L by del q n dot, this is conserved. So, I will write this as constant. But does that help us? Oh, it does not. See, what happens is in the Lagrangian you have q, it is a function of q dot and t. So, even if the value of P n remains constant through the motion, the q dot variable, q n dot variable which appears in the Lagrangian, that is not constant, which means we do not have advantage in the functional form of the Lagrangian, but in the Hamiltonian it definitely has. In the Hamiltonian, what happens is your one coordinate is absent. So, if I write Hamiltonian, which is function of q1, and we know that q n is absent from the Hamiltonian. So, it is up to q n minus 1. After that, I will write p 1 to p n minus 1, and the last variable p n, we know that is just a constant through the motion, which means if I equate this to alpha, I can just substitute alpha there, and of course, it is a function of time t2, and time t. So, the Hamiltonian here now looks like a effective Hamiltonian for n minus 1 degrees of freedom, okay, some sort of a effective. And then if I write the Hamilton's equations, I get q I dot is partial with respect to p I, and p I dot is minus of partial of h with respect to q I, but I only need to compute this for I going from 1 to n minus 1. What about the last variable? P n is anyway constant. How do I find q n? But you already know q n dot. The q n dot is or can be obtained by simply taking partial derivative of h with respect to alpha, and that is it. We need to just solve this for q n. So, this is how the procedure or the canonical variables and corresponding conjugate momenta being constant will reduce the effective Hamiltonian to number of degrees of freedom for which so this procedure will reduce the number of degrees by number of canonical coordinates, number of cyclic coordinates. Okay. Let me apply this procedure for a general case. Let me say that we have a system in which there are n degrees of freedom. Out of this n degrees of freedom, some of those are cyclic. So, what I will do is I will rearrange those variables. I can do a coordinate transformation for it, rearrange those variables, so that the cyclic variables are at the end of the list. So, if there are n degrees of freedom and you have coordinates q 1, q 2 and so on, let us say all those coordinates from s plus 1 to q n. These coordinates here. Okay. So, the first s coordinates are not cyclic, the remaining n minus s coordinates are cyclic. Okay. Now, what I am going to do is I am going to define a new quantity just like Lagrangian Hamiltonian. I will define a Routhian. So, define a Routhian denoted by letter R. Okay. This is a function of q 1 to q s, then q 1 dot to q s dot, and for the remaining variables you take a Legendre transform of this. Remember what we did for Lagrangian to Hamiltonian transformation, we took the Legendre transform of Lagrangian with respect to all the q dot variables. Now, what we are going to do is this: we will not take the Legendre transform with respect to all q dot variables, but only those which are cyclic. So, the remaining ones will appear in the form of Ps plus 1 all the way up to Pl and T, and define this because we are taking Legendre transform. This is summation over Pi Qi dot minus Lagrangian, but this summation over I goes from s plus 1 to n. Okay. This is Routhian. Now, you can clearly see the advantage of this. Out of these ones are constants. Okay. So, effectively you have only S equations, S second order differential equations. So, the equations of motions now are written as d by dt of del r by del q I dot minus del r by del q I is equal to 0, but only for I going from 1 to s. And what happens for the remaining ones? Remember, you have all these are constants. So, q I dot will be equal to derivative of with respect to p I, and this is for I going from r going from s plus 1 to n. Okay. Let me take one example for this. If I take one example, let us say example of symmetric potential. So, a particle moving in a plane under the influence of a potential which depends only on variable r and does not depend on the variable theta. So, the Lagrangian here is half m r dot square plus r square theta dot square minus u of r. Okay. This is the Lagrangian. Immediately we see variable theta is cyclic. So, because theta is cyclic, we know that p theta, which is equal to del L by del theta dot, and this would be equal to m r square theta dot, and this must be equal to constant. I am going to put that constant as Lz. Now, let us construct the Rauthian. So, the Rauthian R will be given by, in this case of course, there is only one variable. So, it is p theta into theta dot minus the Lagrangian, and we can immediately calculate this. This is nothing but p theta square divided by m r square minus, so the Lagrangian is half m r dot square plus r square theta dot square minus u of r. Okay. This simplifies to, so this will be p theta square by 2 m r square minus half m I dot square and plus u r. Okay. So, this is your Rauthian. And how do I construct the equation of motion? There is only one equation of motion to be constructed here, which is d by dt of del r over del r dot minus del r over r is equal to 0, and this we can immediately calculate. Remember, p theta is a Lz, it is a constant. So, this equation will turn out to be, so this will become minus m r double dot minus, now here you would get p theta square by m r cube, okay. And then because there is a minus sign, so become and minus del u by del r is equal to 0. And this is of course the same Lagrangian equation which you would have gotten, except that we realize that p theta is simply a constant which we are going to write it as Lz square. And the second equation, we of course need theta dot, which is del r by del, so p theta, and that is immediately computed as p theta by m r square. And remember, we will write this as Lz by mr square. So, first to solve the r equation, and then of course, when you put it in this, you can also solve the theta equation. And when is this really useful? This is of course useful when you have a system with large number of degrees of freedom, and considerable number of those are cyclic. So, essentially this procedure, which is called as the Routh's procedure or Routhian procedure, this is really of importance to mechanical engineers. We of course will not in physics will not be using this very often. Okay. Now, I will end this week with one nice example, which again illustrates all the ideas that we have learned till now.